Hello. So today we'll discuss about the fundamentals of solid state. So before going to that, we should know that part 30 the definition of a solid substances. A solid is defined as that form of matter in which the constituent particles, that means the atoms, ions, or molecules are held so strongly that they cannot easily move past each other. So we know that the any type of substances, suppose if you will consider any type of solid substances, it will made up of either atoms, ions, or molecules. So they are held so strongly that they cannot easily move past each other. So that is a form which has rigidity and possess definite shape and definite volume. So that is the definition of solid. Now coming to characteristics properties. So now we'll discuss the characteristics properties of solid substances. They have definite shape and definite volume. So this is the first characteristics property. The solids have a definite shape and solids have a definite shape. Why they have a definite shape? It is due to the fact that the constituent particles cannot possess enough energy to move about to keep up different positions. So as the free movement of the constituent particles are not allowed, so they possess a definite shape. And the definite volume of solid is due to the close packing of molecules and strong range of intermolecular forces between them. Now coming to the second property, so they possesses high density and low compressibility due to close packing of particles, which eliminate the free space between the molecules, and that's why they possesses high density and low compressibility. Now, the next property is very slow diffusion. So, the diffusion of a solid is negligible or rather very slow as compared to the permanent position from which they do not move easily. Now, coming to vapor pressure, the vapor pressure of the solid is almost negligible or extremely less as compared to the vapor pressure of liquids at definite temperature. Now coming to melting point, solids have a definite melting point depending on the strength of binding energy. So this type of property is particularly observed in case of crystalline solids. However, in case of some amorphous solids, the melting points are not sharp or not definite. Now coming to definition, a solid is defined as a form of matter in which the atoms, ions, or molecules, that means in which the constituent particles, in which the constituent particles are held so strongly that they cannot easily move past each other, that is in a form which has rigidity and possesses a definite shape and definite volume. So this is the definition of solid. Now coming to the two different types of solid substances, the classification of different types of solid substances. So the solid substances are classified into two types. The first one is amorphous solid and the second one is crystalline solid. So first we'll discuss about the amorphous solid.
ଦୁଇଟା ଯାକ ଦେଇଛି ଜାଣିଲ ନାନୀ କ୍ଲାସ୍ ଆରମ୍ଭ ହେଲାଣି ଦୁଇଟା ଯାକ ଦେଇଛି ସିଟି ଦୁଇଟା ଦେଇଛି
Hello.
ନା ମ ହାତ ହବନି
Okay. So first we'll discuss about the amorphous solid. In the amorphous solid, the arrangement of constituent particles are not in regular but have a, but they are so the constituent particles are arranged in haphazard manner. Although the solids possesses some mechanical properties, for example, although these type of solids possesses some mechanical properties, for example, so rigidity, incompressibility, refractive index, etc., but they do not have characteristic shape of geometrical forms, right? So these are the ca- uh, 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 characteristics properties of the amorphous substances. That means they do not have any type of characteristic shape or geometrical forms. Now coming to the other properties of amorphous solids. The amorphous solids in many respects the resembles with liquids which flow very slowly at room temperature. That means the properties of the amorphous solid is almost similar to the properties of the very slow flowing liquid. and they are regarded as supercooled liquid. So that's why the amorphous solids are also considered as supercooled liquid, in which the cohesive forces holding the molecules together are so great that the material is rigid, but there is no regularity of the structure. Example of amorphous solid: glass, rubber, plastic, etc. Now coming to crystalline solid. So in crystalline solid, the constituent particles are arranged themselves in a regular manner and throughout the entire three-dimensional network, and the ordered arrangement of the ordered arrangement of the constituent particles, that is atoms, ions, or molecules in case of crystalline solid, extends over a large distance. Thus, crystalline solids have a large range order, and a crystalline solid consists of large number of units called crystals. So, in the crystalline solids, you will observe that a particular geometrical unit will be regularly repeated and repeated one upon one to form a giant crystal, and the smallest geometrical unit which is repeated one upon one, so that is known as unit cell. A crystal is defined as a solid figure which has a definite geometrical shape with the fact with flat faces and sharp edges. So now we'll discuss the difference between crystalline and amorphous solid. So now coming to the first different is nothing but that is the definition. So the definition of crystalline solid: they have a definite and a regular arrangement due to definite and orderly arrangement of constituent particles, that is atoms, ions, or molecules in three-dimensional space. But in case of amorphous solid, they do not have any pattern of arrangement of atoms, ions, or molecules, uh, uh, and thus they do not have any definite geometrical shape. Now coming to the second definition, they have sharp melting point and change abruptly into liquids. But in case of amorphous solid, they do not have sharp melting point and do not change abruptly into liquids. Sharp melting point means, suppose we will consider any solid substance and suppose we will take the example of any solid substance. Let the melting point of that solid substance is 100 degree Celsius. That means at 99 degree Celsius, so the substance will be in the solid state, and at 101 degree Celsius, suddenly that will be converted into liquid state. So at 101 degree Celsius, that will be converted into liquid. At 99 degree Celsius, that will be in the solid state. So sharp melting point means the entire solid substances will converted into liquid at a particular temperature, so that is known as sharp melting point. So this sharp melting point characteristic property will be observed for crystalline solid, but in case of amorphous solid, so there will be a range of melting points. Suppose if we take one example of amorphous solid and its melting point is around 100 degrees Celsius, that means that is in the range of 95 degrees Celsius to 105 degrees Celsius. So there will be a range of melting point. So that is for amorphous solid. Now coming to another important property, that is called anisotropic. The crystalline solids are anisotropic, but amorphous solids are isotropic. Isotropic means all the physical properties like refractive index, coefficient of thermal expansion, electrical properties, electrical conductivity, thermal conductivity, etc. So these physical properties are same in all directions of amorphous solid. So for if we measure these physical properties in any directions, if the substance will be amorphous solid, that will give rise to same result. But in case of crystalline solid, so these physical properties, just like refractive index, coefficient of thermal expansion, electrical and thermal conductivity, are different in different directions. For example, if you consider any type of crystalline solid, and so this is the arrangement of crystalline solid where this sign belongs to cation and the circle sign belongs to anion. So here there is a regular arrangement of positively charged cation and negatively charged anion in the solid. Now this is one example of a crystalline solid. Now, if we will measure the electrical conductivity of this crystalline solid, suppose if we will measure the electrical conductivity in the direction of AB and again measure the electrical conductivity in the direction of CD, you will observe that in both the direction the electrical conductivity will be different. Why? If you are measuring the electrical conductivity in the direction of AB, you can see that in that direction only one side contains all cations and the opposite side, the other side of the direction contains all anions. But in case of direction CD, you will find that both cations and anions are present in equal concentration in both the sides of that direction. So that's why when you will measure the electrical conductivity in the direction CD, it will be not influenced by presence of cation and anions inside the ionic solid. But when you will measure the electrical conductivity in every direction, that will definitely influence, and hence in both the direction that will give rise to different results. So these type of properties are called anisotropic properties. But in case of any amorphous substance, if we measure electrical properties in any direction, that will give rise to same result. So if you measure the properties in any direction, you will get same result. So that is called isotropic. Thus, amorphous solids are isotropic, but crystalline solids are anisotropic. Now coming to the next property, that is called cleave property. So the crystalline solids can be cleaved sharply along definite plane. So that means it will break the crystal any crystalline solid, so that will break into flat surface, and so the breaking surface will be a flat surface. But in case of amorphous solids give irregular, fractured or rough surface upon breaking. Now coming to another property. So the next property is crystalline. Crystals are bound by planes of faces, and these the angle between any two faces is called interfacial angle. For a given crystalline solid, it is the definite angle and remains always constant, no matter how the faces develop. So how the face of the crystalline solid will develop, but the angle between two particular faces will be remain constant. However, the faces develop, but the angle between two particular faces will be remain constant. That is, the interfacial angle will be remain constant. So when crystalline solid is hammered, it break up into the smaller crystals of the same geometrical space and same interfacial angle. So, in case of crystalline solid, whether you will take a small crystal or a developed or big crystal, but the interfacial angle will remain same. Now, coming to amorphous solids, do not have any well-defined faces or planes, and hence they do not possess any type of interfacial angle. So, this type of property will not observed in case of amorphous solid. Now coming to classification, after that we will discuss only for crystalline solids, because in crystalline solids, so they have definite geometrical arrangement and definite shape and definite arrangement of constituent particles. So then coming to the classification of crystalline solids, the crystalline solids are classified into four types. The first one is ionic solid. In the ionic solid, the constituent particles are ions which are held together by electrostatic forces. So for ionic solid, the constituent particles are oppositely charged ions, and the oppositely charged ions are held together by electrostatic forces of attraction. The arrangement of these oppositely charged ion in such a way that the cations have anion in their nearest neighbor. So that means one cation is surrounded by anion only, and similarly one anion will be surrounded by only cation. The number of oppositely charged ion surrounded by an ion in its is termed the number of oppositely charged ions surrounding an ion is termed as its coordination number. That means the number of positively charged ions present around one negatively charged ion is known as its the coordination number of the cation, and similarly the number of negatively charged ions around a positively charged ion is known as the coordination number of the cation, and similar way we can also tell the coordination number of the anion. Now, due to strong and non-directional electrostatic interaction, the ionic solids are hard, brittle, and possesses high melting and boiling points. So we know that in case of ionic solid, the constituent particles are oppositely charged ions. As the constituent particles are oppositely charged ions, so they are held together by strong electrostatic forces of interaction, and due to this, so the ionic solids are hard, they are brittle, and possesses high melting and boiling point. And again, they are bad conductors of electricity in the solid state. Ionic solids are bad conductor of electricity in the solid state, but they are good conductor in the molten state. So here the example of some ionic solids are there. Now coming to covalent solid. So in case of covalent solid, the constituent particles are atoms, and so in case of ionic solid, the constituent particles were oppositely charged ions, that is cations and anions. Now in case of second type, that is covalent solid, the constituent particles are atoms, and here the constituent particles are arranged themselves or are held together by covalent bonds. So here the constituent particles are atoms and they held together by covalent bonds. So the bonds in the covalent solids extend throughout the crystal, and this result in the formation of a giant three-dimensional structure. The coordination bonds in the covalent solid will extend up to infinite number of atoms, and hence they will form a giant three-dimensional structure. So the covalent solids are again classified into two types. In the first one, if the covalent bonds extend in three dimension, forming a giant interlocking structure. So if the covalent bond extend in three dimension, and the another type is if the covalent bond will extend in two dimension. So first we'll discuss if the covalent bond will extend in three dimension, forming a giant interlocking structure. Example of such type of covalent solids are diamond, silicon carbide, aluminum, etc. So here we will discuss the example of diamond, in which the carbon atom, the constituent particles are carbon atom. So the constituent particles of diamond are carbon atoms, and in the diamond every carbon atom is tetrahedrally bonded with four other carbon atoms. So so they will, suppose you will consider this carbon first carbon atom, so that is tetrahedrally bonded with four other carbon atoms by sp3 hybridization. So by sp3 hybridization, each carbon atom is tetrahedrally bonded with four other carbon atoms, and hence they will form a three-dimensional hexagonal crystal structure. So in which the atoms are held together by strong covalent bond. Thus, these solids are very hard. For example, diamond is the hardest structure known till now. So there is no mobile electrons in these solids, and hence they are bad conductor of heat and electricity. So that means no free electron will be there in this structure. There will be no free electron, and hence they are bad conductor of heat and electricity. Now they have very high melting and boiling point. Now coming to the next type. So in the next type, the covalent bonds extend in two dimension. If the covalent bond will extend in uh, two dimension, they will form a giant layer structure. So these layers are held together by van der Waals forces. Example of these solids: graphite, boron nitride, cadmium iodide, etc. Features: these solids are soft and good conductors of heat and good conductors of electricity. These solids are generally soft and good conductors of electricity, and they are flaky in nature and slippery in nature. So example of this solid is graphite. So it has a two-dimensional sheet structure. Each carbon atom is covalently bonded to three other carbon atoms in hexagonal planar structure. So out of the four valence electrons of the carbon, three are used in forming covalent bonding, and one spare electron with each carbon atom makes the graphite a good conductor of electricity. So in this structure, you can see each carbon atom each each carbon atom is bonded to three other carbon atoms by sp2 hybridization, and hence each carbon the structure of the sp2 hybrid orbital will become trigonal planar. That means planar structure, and it will arrange the all the planars, so that will form hexagonal layer structure, right? And apart from that, every carbon atom contains one spare electron, because the hybridization of every carbon atom is sp2 hybridization. Every carbon atom is bonded with sp2 hybridization, and there will be a spare electron associated with every carbon atom. So the carbon atoms will be arranged in a layer structure or planar structure. Now coming to arcs. So in between one layer, the bonds are very strong bond. That means in between a particular layer, the carbon atoms are bonded by sp3 hybridization to form covalent bonds. But if we will consider the forces of interaction, now if you will consider the carbon atoms present in a particular layer, so in a particular layer the carbon atoms are bonded by very strong covalent bond, sp2 hybridization forming sp2 hybridization, so they will form a layer like structure. So the covalent bond between the carbon atoms within a particular layer is very strong. But whenever we will consider the bond between two layers, the bond between the layers, and in this case the bond is a weak van der Waals forces, so that one layer can easily slip over another layer, right? And that's why graphite so the planar structure, out of the four valence electrons of carbon, they are used in covalent bonding, three are used in covalent bonding. So we know that four valence electrons are there in carbon, but out of the four valence electron, three electrons are used forming covalent bonds, and one spare electron with each carbon atom makes the graphite a good conductor of electricity. Now coming to the third category, so that is called molecular solid. So in the molecular solid, the constituent particles are small, but molecules which are held together by dipole-dipole interaction. So in molecular solid, the constituent. So first we have discussed in ionic solid. In ionic solid, the constituent particles are oppositely charged cations and anions. That is oppositely charged ions. Now after that, in covalent solid, the constituent particles are atoms. Now in the third category, the constituent. So that is molecular solid. So in the molecular solid, the constituent particles are small molecules which are held together by dipole-dipole interaction. In the first category, the constituent particles were ion, and the interaction was electrostatic interaction between them. In the second category, the constituent particles are atoms, and the interaction was covalent bonding. Now, in the third category, the constituent particles are molecules, and in this case, the interaction is comparatively weak dipole-dipole interaction between the molecules, or van der Waals forces of interaction between the molecules. Now, as these dipole-dipole interaction or van der Waals forces of interactions are very weak interactions, three category of molecular solids are there. The first one is non-polar molecular solid. So here the constituent particles are atoms like noble gases. So non-polar bond will be formed for noble gases, and for for nonpolar molecules like H2 molecules, Cl2, I2, methane, etc. So these particles are held by weak dispersion forces or London forces. The solids are very soft and non-conductor, have low melting and boiling point. They are normally in the gaseous state at room temperature. So that means if you want to find the solid substances of these substances, the the solid state of these substances, you have to go to very low temperature, that is minus 100, minus 150, minus 160 degrees Celsius, right? But at room temperature, these solids are generally in the gaseous state. Now coming to the second category, that is polar molecular solid. Here the in the polar molecular solid, the constituent particles are polar molecules. For example, HCl, sulfur dioxide, and here the particles are held together by dipole-dipole interaction. And in the first case, the forces of interaction was van der Waals forces of interaction, that was the least forces of interaction. And in the second case, that is for polar molecular solid, the forces of interaction is dipole-dipole interaction, comparatively higher interaction, but still that is the interaction is very less. But that is comparatively higher interaction than van der Waals interaction. So these solids are soft, non-conductors, have comparatively higher melting and boiling point, and they are generally gases or liquids at room temperature. Now coming to hydrogen bonded molecular solid, and here the constituent particles are molecules which will contain partially positively charged hydrogen atom, and thus the molecules which can form hydrogen bond. That means there should be one partial positively hydrogen atom and partially negatively charged fluorine or oxygen or neon should be there. So if the molecule will contain this type of partially positively charged hydrogen atom and partially negatively charged fluorine or oxygen or nitrogen, then there is a possibility of formation of hydrogen bond between the molecules. And if so they will form hydrogen bond between the molecules in solid state. So these solids are called hydrogen bonded molecular solid. Examples of hydrogen bonded molecular solid, that is ice. So in the ice, the constituent particle is water molecule, where the water molecules are hydrogen bonded with other water molecules to form the solid structure ice. And here the process of interaction is comparatively that is the process of interaction between the molecule is called hydrogen bonding, and that is comparatively more stronger. Now coming to metallic solid. The constituent particle in the metallic solid are positively charged metals, that is called as kernels. So these positively charged metals are formed by the removal of valence electrons from the atomic metal. By removal of all the valence electrons from the metallic atom. So if you remove all the valence electrons from the metallic atom, then that will become kernels, right? So in case of metallic solid, the constituent particles are kernels and mobile electrons. Mobile electrons means when all the valence electrons of the metallic atom will be removed, so they will be inside the metallic crystal, and there are free electrons, so they can easily move from one position to another position within the metallic crystal, and hence these are also called as mobile electrons. And in this solid, the forces of interaction, the forces that bind the cation and electrons in the metallic electrons is the metallic bond. So here there will be interaction between the positively charged cation or kernels of the metal and mobile electron. So this is the interaction in which the metallic solid will be formed. That is the interaction between the positively charged kernel and the mobile electrons. So these solids have very high electrical and thermal conductivity. They possess lustrous and they are highly malleable and ductile in nature. They have high density and high melting and boiling points. So here this is the example of a metallic solid. You can see in this metallic solid the positively charged metal cations are there, so they will maintain their position, fixed position, and so these are called as kernels, and these are formed by the removal of all the valence electrons from the metal cation. So when all the valence electron will be removed from this metal cation, from this metal atom to form metal cation Mn plus. So these electrons will remain present inside the crystal and hence they will behave as mobile electrons or free electrons. You can see if this is a metallic crystal and these are the positions of the kernels. So the position of the kernels are fixed. So they will at the lattice point, right, to form a crystalline solid. And here, so these are the position of the mobile electrons. So these are mobile electron means they will flow continuously from one place of the crystal into another place. And here also the interaction or the forces of interaction to form the metallic solid is electrostatic forces of interaction between the kernels and the mobile electrons. Now, so here we have discussed about the classification of crystalline solids. So now we will discuss about the crystal lattice and unit cell. First, we will discuss space lattice. So the space lattice, it is a three-dimensional arrangement of identical point in space which represent how the constituent particles are arranged in a three-dimensional crystal. So space lattice means it is the three-dimensional arrangement of identical point in space, so that that will show how a similar how the constituent particle, that means how the atoms, ions or molecules will be arranged in a crystal. The geometrical form consisting only a regular array of points in space is called lattice or space lattice, or it can be defined as an array of points showing how the molecules, atoms, or ions are arranged in different sites in a three-dimensional space. The sites which are occupied by the constituent units, that is atoms, ions, or molecules, so these are called as lattice sites or lattice point. So in the any type of crystalline solid, so people consider a crystal. So in that crystal, there is a regular arrangement of lattice point or a regular geometrical arrangement of lattice point. So it is lattice point means it is the position of the constituent particles to make the crystal. So that means it is the position of the cations and anions or the atoms, if covalent solid will be there, or if molecular solid will be there, that will be molecule, and if metallic solid will be there, that will be kernels. So these are the position of the kernels which are the basis to form a giant crystal. Now coming to unit cell. Unit cell, a space lattice can be subdivided into a number of small cells. A space lattice can be subdivided into a number of small cells known as unit cells. So it can be defined as the smallest repeating unit in the space, which when repeated over and over again, resulting in a crystal of the given substance, or it is the smallest block or geometrical figure from which the entire crystal can be built up by translational repetition in three-dimensional space. So unit cell is the smallest geometrical unit of a crystal which repeated over and over again to form the three-dimensional crystal. Now coming to parameters of unit cell, what are the different parameters of a unit cell? A unit cell is characterized by its dimension along the three edges. Suppose if that will be characterized by dimension, if you have to consider three edges, that is edge A, B, and C, and angle between them. So these are the three different parameters. So that is edge length of that unit cell along x-axis, along y-axis, and along z-axis. That is ABC. And again in the second, another three parameters are there. That is angle, edge, angle alpha, alpha, beta, and gamma. So between the so these angles are the angles between the edges. So alpha is the angle between B and C, beta is angle between A and C, and gamma is the angle between A and B. And hence a unit cell is characterized by six parameters: A, B, C, and alpha, beta, gamma. Now coming to types of unit cell. So the unit cells are classified into four types. All the unit cells are classified into four types. First one is primitive or simple unit cell. Primitive or simple unit cell means the constituent particles will present only at the corner of the unit cell. So the constituent particles are present only at the corner of the unit cell, then that is called primitive or simple unit cell. Now, if the constituent particles will present, the constituent particles will present at the corners as well as the center of the unit cell or the center of the body of the unit cell, then that is called body centered unit cell. Now coming to face centered unit cell. If the constituent particles will be present at the corners as well as at the center of each faces, then the arrangement is called face centered unit cell. Now coming to end center unit cell. If the constituent particles will be present at the corners as well as the center of any two opposite faces, then that is called end center unit cell, or that is also called base center unit cell. So here the constituent particle will be present at the corners as well as center of any two opposite faces, and that two opposite faces will be called as base, and hence this type of arrangement is also called base centered arrangement. And similar way, so there are four types of unit cells. First one is simple or primitive unit cell, the second one is body centered unit cell, the third one is face centered unit cell, and the fourth one is end centered or base centered unit cell. Now coming to crystal system, there are seven types of basic or primitive unit cells that have been recognized between crystal, and the seven unit cells or the seven basic crystal systems are cubic, tetragonal, orthogonal, monoclinic, triclinic, hexagonal, and rhombohedral. So in this type of arrangement, you can see that so the symmetry of the arrangement gradually decreases. So these are the seven basic crystal systems. Now within the seven basic crystal system, we will find the Bravais lattice. Now coming to what is Bravais lattice or Bravais space lattice. August Bravais pointed out that there can be only 14 different ways in which the similar points can be arranged. So there can be only 14 different ways in which the similar points can be arranged in three-dimensional space. Thus, the total number of space lattice belonging to all the seven crystal system is 14. So here in this table, we will discuss about the seven basic crystal systems and the 14 Bravais lattice within the seven basic crystal systems. So we will arrange the seven basic crystal systems from the most symmetric form to the least symmetric form, and it will be very so you have to remember all the seven basic crystal systems, and along with their axial distances or axial angles, that is axial parameters. So there is a very short way to remember. So there is a very short formula to remember this. So that is this one, that is Q our mother. So from this, first one is cubic, and second one is tetragonal, third one is orthorhombic, the fourth one is monoclinic, fifth one is trigonal, sorry, triclinic, sixth one is hexagonal, and the seventh one is rhombohedral. And the other name of rhombohedral, that is called trigonal. So we will go from the first one. First one is cubic, so that is the most symmetric arrangement, right? So in cubic crystal system, the axial distances are A equals to B equals to C, and the axial angles, that is alpha E equals to beta equals to gamma equals to 90 degree. Examples are sodium chloride, potassium chloride, zinc sulfide, etc. And in the cubic crystal, you will find, so the cubic crystals are again classified into three Bravais lattice, that is primitive. The second one is body centered cubic. The third one is face centered cubic. So here three different types of cubic systems are there. First one is primitive cubic, second one is BCC, that is body centered cubic, the third one is FCC, that is face centered cubic. Now coming to the next arrangement. So in this cubic arrangement, so that is the most symmetrical form, and hence the edge length, all the edge length are equal, that is A equals to B equals to C, and all the axial angles are also equals to 90 degree, that is alpha equal to beta equals to 90 degree. Now if we move to the next one, that is a tetragonal. So in tetragonal arrangement only one symmetry will be lost. So here one symmetry will be lost, so that is A equals to B is not equals to C, and the remaining alpha equals to beta equals to gamma equals to 90 degree. And the tetragonal system is also classified into two Bravais lattice. The first one is primitive and the second one is body center. Now coming to orthorhombic. So in the orthorhombic system, another one symmetry will be lost. So here alpha is not, A is not equals to B is not equals to C, but alpha equals to beta equals to gamma equals to 90 degree. And the Bravais lattice for the orthorhombic crystal, there are four Bravais lattice. First one is primitive, then body center, then face center, then end center. So that means all types of Bravais lattice are present in the orthorhombic system. Now coming to monoclinic. So in the monoclinic, A is not equals to C is not equals to A is not equals to B is not equals to C, and here again one symmetry will be lost from the axial angles. So that is alpha equals to gamma equals to 90 degree, but beta is not equals to 90 degree. So that is called a monoclinic system. So in the monoclinic system, there will be two Bravais lattice, primitive and base centered or end center. Now coming to the most unsymmetrical form, that is called a triclinic system. So in the triclinic system, A is not equal to B is not equal to C. Similarly, alpha is not equal to beta is not equal to gamma is not equal to 90 degree. So the example of the system is potassium dichromate, copper sulfate. So these are the example of triclinic system, and that is the most unsymmetrical form. And apart from these five basic crystal system, another two basic crystal systems are also there. So that is the first one is hexagonal. So it has only one Bravais lattice, that is primitive. So in the hexagonal system, A is equals to B is not equals to C, and alpha equals to beta equals to 90 degree, but gamma equals to 120 degree. So here these you will find at the base alpha equals to beta equals to 90 degree. So that will be a hexagon at the base, and that hexagon will be extended into form a three-dimensional structure. And next one is rhombohedral or trigonal. So the rhombohedral basic crystal system also only one Bravais lattice, that is called primitive. That means only the constituent particles will be present only at the corners. So in this system, in the rhombohedral system, so A equals to B equals to C, alpha equals to beta equals to gamma, but they that does not equals to 90 degree. So this type of system is also called as rhombohedral or trigonal. So these are the four basics, seven basic crystal systems, and the 14 Bravais lattice. You can see the 14 Bravais lattice arises from, because for cubic three Bravais lattice are there. For cubic the number of Bravais lattice 3, for tetragonal 2, so that is 3 plus 2 5, for orthorhombic that is 4, 5 plus 4 9, for monoclinic 2, 9 plus 2 11, for triclinic 1 12, for hexagonal 1 13, for rhombohedral 1 that is 14. So in this way we can characterize the 14 Bravais lattice. Now coming to the next one, the next one is calculation of number of particles in a unit cell. If you want to calculate the number of constituent particles present in a particular unit cell, so that is calculation of number of particles in a unit cell. Now each corner atom in a unit cell is equally shared by 8 unit cells. Therefore, the contribution made by each corner atom per unit cell equals to 1 by 8 atom. So if we'll consider any spherical, yes. So here you can see here, this is a cubical, simple cubic arrangement. In this simple cubic arrangement, each corner contains one constituent particle. So this is the arrangement we are drawing for our calculation. But the actual arrangement will be like this. This is not the actual arrangement because we know that in the solid state, the constituent particles are very closely packed. So in the actual arrangement, you will find that all the constituent particles are almost touching with one another. So actual arrangement is like this. So out of which if will connect the center of the eight cubes, the center of the eight spheres. Sphere means constituent particle because here we are considering the constituent particles to be spherical nature. So it will connect the center of the eight spheres. So there will be that will form a regular cubical arrangement will be formed, and you can see each if we consider how many constituent particles are present at each corner, so it will be 1/8 of the sphere because each corner, because we know that in a crystal the unit cells are infinitely arranged in three-dimensional space. So that means the unit cells are regularly arranged in towards left, towards right, towards upper, towards inwards, outwards, upward, downward, like this. So another unit cell will be there. Similarly, another two unit cell will be there, right? So that means if we consider the three-dimensional arrangement in this manner, you can see that each corner will be shared by eight unit cells, and hence if we remove one unit cell, then the number of constituent particles present at each corner will be 1/8 of the unit cell. So each corner or atom of the unit cell will be equally shared by 8 unit cells. Therefore, the contribution made by each corner atom per unit cell equals to 1/8 of the atom. Similarly, in case of phase center, for each phase center atom, each phase of the unit cell is shared by 2 unit cells, so that the contribution made by each phase center atom per unit cell equals to 1/2, half of the atom. Now, if we'll consider edge center, each edge atom is shared by 4 unit cells. So the contribution made by each edge center atom equals to 1/4 edge center atom per unit cell equals to 1/4 of the atom. And similarly, for the body center atom, as the body center atom is not shared by any other unit cell, so the contribution made by the body center atom per unit cell equals to 1. And hence, so this is the formula for Z. Total number of particles present in a unit cell, that is called Z. Here Z is not atomic number, right? So here Z is not the atomic number. So here Z is total number of particles in a unit cell, that is equals to 1/8 into number of particles occupied by the corner, because we know that for every corner you will find the total fraction towards that unit cell coming from every corner, that will be 1/8. So 1/8 into occupied by the corner, now plus 1/4 into occupied by the edge center, now plus 1/2 into occupied by the face center, plus 1 occupied by the body center. So by using this formula, you can calculate the number of constituent particles present per unit cell. Now, for example, if you calculate the Z value of simple or primitive cubic unit cell, we know that for primitive unit cell, the constituent particles will present are only present at the corners. So, for primitive unit cell, Z equals to 1/8 into 8, that is equals to 1. And similarly, for body centered unit cell, Z equals to 1/8 into 8, so that is coming from the 8 corners, and another one from the center, from inside the unit cell or from the center of the body, that is called body center. So complete one will come. So total number of constituent particles present in body centered cubic unit cell, that is equals to 2. Similarly, if you consider the number of constituent particles at face-centered cubic unit cell, so for each face-centered cubic unit cell, Z equals to 1 by 8 into 8, because in every arrangement the corner in the constituent particle will be present at the corner of the unit cell. So for face-centered unit cell, Z equal to 1 by 8 into 8 plus, and in the unit cell there will be 6 faces will be there. So each face will be shared by 2 unit cells, and hence if we consider the fraction of the constituent particle present at a particular face, that will become half. So in the, for face center cubic unit cell, the contribution from the corner will be 1 by 8 into 8, and the contribution from the face will be half into 6, and total will become 4. Now coming to the relationship between the nearest neighbor distance d and the radius of the atom r. So here we will discuss the relationship between the nearest neighbor distance. So nearest neighbor distance means it is the smallest distance between two spheres or two constituent particles. So whenever we will calculate the distance between two constituent particles, we will calculate the distance, the center of the distance between constituent particles, that is d, and the radius of the atom, that is r, and age of the unit cell, that is a, in the cubic system. So here this is the cubic system where edge length of the unit cell, that is a, and radius of the constituent particle. So here we are considering the constituent particle to be spherical nature, so radius of the constituent particles to be r, and edge length of the unit cell a. Now this is the arrangement for calculation, but this is the actual arrangement. In this actual arrangement, people join the center of the sphere, so there will, so that will form cubical arrangement will be formed, and that is called simple cubic or primitive cubic unit cell. So here a is the edge length of the unit cell, that is equals to d. So here A equals to D. So D is the nearest neighbor distance. D is the nearest neighbor distance between two particles. That means this distance is called D, and this, as these are arranged in simple cubic arrangement, this distance is also called A. So D equals to A, which is equals to 2R. And if we will write the value of r, that is equals to a by 2, so that is equals to 0.5 a, or r equals to 0.5 a. Now next one is BCC arrangement. So in the BCC arrangement you can see the, so this is, so this arrangement is as per our calculation, but this is the actual arrangement. So in the actual arrangement, the in the cubic unit cell, you can find each corner will be occupied by the constituent particles, and also the center of the unit cell will be also occupied by constituent particles, that is called BCC arrangement. So when one constituent particle will be present at the center of the unit cell, definitely the unit, the constituent particles which are present at the corners will not touch one another, so they will be apart from one another, and in that case you cannot tell that d equals to a, right? So in order to this, we have to calculate the value of d. So d will be coming out from the half of the body diagonal, so that is called d. So here half of the body diagonal, half of the body diagonal will be considered as d. So here half of the body diagonal will be considered as d, that is the nearest neighbor distance between the two particles, because here the corner particles are not touching with one another, but every corner particle will touch to the body center particle. So that means here A and E are touching with one another, but A and B are not touching, and also B and C are not touching with one another. But A and E are touching with one another. So so the nearest neighbor distance is AE, and that is half of the body diagonal. So here we have to first calculate the distance of the body diagonal. In order to calculate the distance of the body diagonal, first we should measure the distance of the face diagonal. So in this arrangement, you see, first we have to calculate AC distance. So here one constituent particle will be there at A, another constituent particle will be at B, and another constituent particle will be at C. So in this right angle triangle, we have to find out AB is A, that is edge length of the unit cubic unit cell A, and similarly BC is A, so the value of AC will be root 2A. So here AC will be, so this is face diagonal and its value will be root 2A. And after that we will calculate the value of AD. So in the right angle triangle ACD, this one is root 2A, root 2A, AC is root 2A, and CD is A. And the value of AD, so we know that if you apply Pythagoras theorem, AD square equals to AC square plus CD square. So the value of AC is root 2A, so root 2A square equals to A square, so that is equal to 3A square, and hence the value of AD equals to root 3A, and the nearest neighbor distance is D, that is half of AD, so that is AE, and here T equals to root 3 by 2A, root 3 by 2A, and again we know that that is equals to 2R, and hence R equals to root 3 by 4A. Now coming to the similar relationship for FCC arrangement. So for FCC arrangement, you can see, and here also all the corner spheres will not touching with one another. So because, so this is the actual arrangement. So in this actual arrangement, you can see the unit cell contains constituent particles at the corners as well as center of each faces. As the center of each faces contain constituent particles, so the corner constituent particles will not touch with one another. So here, in order to calculate the value of nearest neighbor distance, we have to calculate the value of one face diagonal. So half of the face diagonal is nothing but the nearest neighbor distance. So the distance between two nearest the neighbor atom is represented by AB or BC. So here you will find the value of AB or you will find the value of BC. So that is known as nearest neighbor distance. So the distance between the nearest neighbor D equals to AB equals to BC, that is equal to AC by 2. So here you will calculate the value of AC in the right angle triangle. So first we will calculate the value of AC, and here CD equals to A, AD equals to A, and hence the value of BC will be A square plus A square, that is equals to 2A square. So that is the value of BC square. So the value of BC equals to root 2A, and hence, sorry, the value of AC will be root 2A, and the value of BC will be root 2A by 2. So that is 1 by root 2A, and hence that is called nearest neighbor distance D equal to 2R equal to 1 by root 2A. Now coming to the calculation of, so here we will, so I will, so we will break the class for only 5 minutes, and after that again we will start. Hello. Okay. So again, we'll discuss the calculation of percentage of occupied space or packing efficiency in the cubic system. The first one is simple cubic system. So the packing efficiency means the the occupied space by constituent particles divided by total volume. Occupied volume divided by total volume, that is called packing fraction. And whenever you will calculate packing efficiency, so only we will calculate the percentage of occupied volume. So that is occupied volume by total volume into 100. So if you multiply by 100, that will become percentage packing efficiency, and the occupied volume by total volume, that is known as packing fraction. Packing fraction means so that will be a fraction, and packing efficiency means that will be a percentage, right? So first we'll calculate the packing fraction or packing efficiency for simple cubic unit cell. So we know that for simple cubic unit cell, the total number of constituent particles will be 1, that is 8 into 1 by 8. In the 8 corner, you will find constituent particle. Constituent particles are present at each corner, but if you look calculate the contribution made by the constituent particle for one unit cell, that is 1 by 8, and hence the number of atoms per unit cell or the number of constituent particles per unit cell, that is equals to 8 into 1 by 8, that is equals to 1. And here, if we consider the constituent particle to be spherical in nature, with radius of the sphere or atom, if the radius of the sphere or atom equals to r, then the volume of the atom will be 4 by 3 pi r cube. So this is known as the occupied volume. And suppose the edge length of the unit cell equals to a, and hence the total volume, that is equals to the total volume is AQ, the volume of the unit cell, that is AQ. But again, we know that for simple cubic unit cell, A is equals to 2R, that we have taken from the last calculation, because we know that A equals to 2R. So if you put the value of A equals to 2R, so A cube means whole cube of 2R, that is equals to 8R cube, and hence the total volume is 8R cube, but the occupied volume is 4 by 3 pi R cube. So the packing fraction, that is equals to occupied volume by total volume, which is equals to 4 by 3 pi r cube divided by 8 r cube. Then r cube will be cancelled out. So only some constant value will be there, and the value will be 0.5233. So this is known as packing fraction. But if you will measure the packing efficiency, that can be measured in terms of percentage of occupied space. So the percentage of occupied space, or that is packing efficiency, equals to 52.33%. Similarly, we will move to the body centered unit cell. Now for body centered unit cell, so edge length of the unit cell is A, let edge length of the unit cell A, radius of the atom, that is R, and in this unit cell we know that the relationship is like this: A equals to 4 by 3 R, because that relationship we have studied in the previous section. R equals to root 3 by 4A, so A equals to 4 by 3, 4 by root 3 R. So A equals to 4 by root 3 R, right? And then volume of the unit cell, that is equals to A cube, equals to 4 by root 3 R whole cube, that is equals to 64 by 3 root 3 R cube. And the total number of spheres or total number of atoms per unit cell equals to 2. And if R is the radius of the atom, then the volume of the two atoms will be 2 into 4 by 3 pi r cube, and this volume is known as occupied volume, and hence packing fraction equal to occupied volume divided by total volume. So the occupied volume is the 2 into 4 by 3 pi r cube, Total volume is 64 by 3 root 3 r cube, and here pi r cube will be cancelled out. The remaining values are constant value, and that will be calculated to be 0.68, and here that is also fixed. For FCC, for BCC, the fraction, the packing fraction is 0.68, that is fixed, and hence the packing efficiency is 68%. Now coming to face-centered unit cell (FCC), suppose edge length of the unit cell equals to A and radius of the sphere equals to R. Then in this unit cell, the relationship we know that A equals to 2 root 2 R, and hence the volume of the unit cell equals to A cube, that is equals to Q 2 root 2 R whole cube of 2 root 2 R, that is equals to 16 root 2 R cube. And here the number of atoms per unit cell, that is equals to 4, and hence the volume of the 4 atom will be 4 into 4 by 3 pi R cube, and packing fraction equals to occupied volume divided by total volume. So this is the occupied volume, 4 into 4 by 3 pi r cube. Then the total volume will be 16 root 2 r cube, and the value will be 0.7401, that is packing fraction. And if you calculate the packing efficiency, the value will become 74.01%. So this is the table which will summarize the relationship between A, R, D uh, for cubic unit cells, and also the packing fraction of the different cubic unit cells. And now coming to closed packing in solid. After that, we will discuss closed packing in solid. So for closed packing in solid, in order to discuss the closed packing in solid, first we will discuss the closed packing of solid in one dimension. So one dimension closed packing means here the spheres, that is atoms, ions, or molecules, are linear in horizontal rows touching with one another. So this is called one dimensional closed packing. Now coming to two-dimensional closed packing. So for two-dimensional closed packing, so there are two different the two-dimensional closed packing can be formed by two different ways. So the first one is square closed packing. The second one is hexagonal closed packing. So first we'll discuss about the square closed packing. In this arrangement, the rows have vertical and horizontal alignment. That means in square closed packing, you can see all the rows are there will be alignment in horizontal arrangement, also in vertical arrangement. Vertical, the spheres are vertically and horizontally aligned. So that is called square closed packing. So the spheres are packed in form of a square array, and in this packing, the coordination number is 4. Suppose you will consider one sphere, and the question is what is the coordination number of the sphere. So to that sphere, how many spheres are touching? Four spheres are touching to that particular, to that mentioned sphere, and hence coordination number of that mentioned sphere is 4. And if you join the center of the four spheres touching to that mentioned sphere, you will find a square. So these are the four spheres touching to the mentioned sphere, and if you join the center of the four spheres touching to this mentioned sphere, you will find a square, and hence this is called square closed packing. So in the square closed packing, the coordination number is 4. Now coming to hexagonal closed packing. So in the hexagonal closed packing, the rows are arranged so that the spheres of the second row occupy the depression point, the spheres of the first row, and so on. So here you can see, suppose this is the arrangement of the first row A, and here you can find the spheres of B will be present at the depression point of A. So here this is the arrangement A, and these are the depression points. So these positions are called depression point of the first line. This is the depression point, and this point is the depression point. So this is the depression point. So these points are the depression point of the first line. So the spheres of the second line will be placed on the depression points on the spheres of the third line, spheres of the first line, and similarly the spheres of the third line will be placed on the depression point of the spheres of the second line, and so on. The spheres of the third row, and if you arrange this type of arrangement, if you arrange, if you go to infinite arrangement, you can see the spheres of the third row will be vertically aligned with the spheres of the first row. First and third will be vertically aligned, and similarly second and fourth will be vertically aligned. Horizontal alignment is there, but for vertical alignment you will consider second and fourth, and uh, and for first row, first row is vertically aligned with third row. Similarly, second row is vertically aligned with fourth row, and so on. So the spheres of the third row are vertically aligned with the spheres of the first row, and those in the fourth row are vertically aligned with the spheres of the second row. Each sphere is surrounded. Each sphere surrounded hexagonally by six other spheres. Coordination number is 4, and if you join the spheres of the six touching sphere to a particular sphere, suppose this is a mention sphere, and the question is what is the coordination number of that sphere. The coordination number of that sphere is 6. So because six other spheres are touching to that mention sphere, if you join the center of the six spheres touching to this mention sphere, that will form a regular hexagon. So this type of packing gives a hexagonal pattern. In this packing, the coordination number is 6, and the central sphere is in contact with 6 other spheres. So here the coordination number is 6, and there are vacant spaces between the three touching spheres. You will find vacant space between the, suppose this is the three touching spheres, and within the three touching sphere there will be some vacant spaces, and these vacant spaces are called as voids, and in this particular case that is called triangular void, because this void is formed in two dimension when three spheres touch with one another. Now again we will move to the closed packing in three dimension. So first, so the in the three dimension you will see that the closed packing in three dimension will form on the two dimensional array. So in the closed packing in two dimension we have discussed two types of arrangement. One is square closed packing, and another one is hexagonal closed packing. So if we will move the three dimensional arrangement of square closed packing, the arrangement will be called simple cubic structure, because simple cubic structure results when the spheres in the second layer are just placed over the spheres in the first layer, so that the spheres in the two layers are vertically aligned, and this process repeated again and again. So this type of packing has an arrangement of AAA, because all the layers are equivalent, so these layers are called as AAA. And this type of packing, the packing efficiency of this type of packing is only 52%. So that means only 52% of the available volume is occupied by the sphere. In this pattern, each sphere, so so here this is the first layer square closed packing layer, and this is second square closed packing layer, this is third square closed packing layer, this is fourth square closed packing layer. So if you arrange the different layers very closely with one another, so they will form a simple cubic arrangement. And if you calculate the coordination number of the simple cubic arrangement, so the coordination number will be 6. How that will become 6? Suppose we are calculating the coordination number of these spheres. Now suppose we are calculating the coordination number of these spheres. So these spheres on the plane, the sphere is in contact with four other spheres, right? and above the plane the sphere is in contact with one sphere, and below the plane the sphere is in contact with one sphere. So the total coordination number is 6. Now coming to close packing on the base of hexagonal close packed array. The spheres in the base layer are marked as A. Suppose we will discuss the three-dimensional packing in hexagonal close packed, the three-dimensional packing where the base will be hexagonal close packed array, and here the base layer is marked as A, and there are two types of voids or hollows present in the base layer. So the base layer there will be two type of voids. So that is suppose, so these are called as void B, and another type of voids will be void A. So these are void A. So two kinds of voids are there, that is void A and B. The spheres of the second layer can be either placed on the void mark A or B, but it is very difficult, but it is not possible to place the spheres of the second layer on both the voids. You can either place the spheres of the second layer on type A or type B. Now suppose you will place the spheres over void A, then we cannot place the spheres over void B. Again we have to place the spheres over void A, and again we have to place the spheres over void A. That means the void B will remain vacant. So the spheres of the second layer can be either placed on the voids marked A or B, but it is impossible to place the spheres on both the types of voids simultaneously. Now there are two types of voids on the second layer. So now if you arrange the spheres of the second layer on the void type A, so the void A will be closed, and in the second layer you will find it again two new different types of voids. First one is one new void will be formed. Suppose these are the spheres of the dotted. So the dotted spheres are the spheres of the second layer. You can see. So in the second layer, void C are formed. New type of voids are formed. These are called as C. And apart from this, some old layer, old void was there, which was initially named as the B. That is B on the first layer. That is extended to the second layer, and that become D. So the void C, so there will be two types of voids above the void, above the second layer, that is void C and void D. Void C are ordinary, which lie above the spheres of the base layer, and there are two voids D lie on the voids of B of the first layer, and the voids D are in combination of the two voids. Thus one of the first layer and another from the second layer. So these voids D are called as octahedral void. The void D will be formed by extension of void B from the first layer to second layer. So that void is formed by the combination of six pairs and two voids, and that's why that is called octahedral void. Now coming to A and B voids of the first layer and C voids of the second layer are called triangular void, because these voids are formed by the surrounded by four spheres, three spheres, and the simple triangular void in the three-dimensional arrangement is surrounded by four spheres, and that is called tetrahedral void, because if you will calculate if you will join the center of the four spheres, that will form a regular tetrahedron. Now coming to build up the third layer, we have two alternatives. The first alternative is that we can place the spheres over void, the spheres of the third layer over void C or over void D. If we put the spheres of the third layer over void C, then the third layer will be equivalent to first layer, and if we move on this type of arrangement, the arrangement will be called AB arrangement or hexagonal close packing arrangement. Now another option is there, if we put the spheres over void D, then that will give rise to a new layer, capital C, because initially two layers were there, so that will form a new layer capital C, and this type of arrangement will be called ABC, ABC, ABC arrangement. So that is called HCP or hexagonal closed packed arrangement. So here this is the hexagonal HCP or hexagonal closed packed arrangement, that is called AB, AB, AB arrangement, and this is called cubic closed packing or CCP arrangement. So here the first, second, and third layers will not be different. But first layer is equivalent to fourth layer, second layer is equivalent to fifth layer, and third layer is equivalent to sixth layer. And in like way, so the different layers will be arranged. Now coming to voids, so there are two types of voids are there. One is called as tetrahedral void. So the tetrahedral void is formed by the close packing of four spheres. So this is the angle view. If you do the front view, you can see. So these are the three spheres touching with one another to form a triangular hole. And if you place another sphere to cover the triangular hole, that will become tetrahedral void or tetrahedral hole. And this is the octahedral void or octahedral hole. The octahedral void, we know that that will be formed between the two layers, right? So here that is called octahedral site. So the octahedral site is enclosed by six spheres, and if you join the center of the six spheres, so one regular octahedron will be formed. Now then derivation of relationship between radius r of the tetrahedral void and radius capital R of the sphere. So here the radius of the sphere is considered to be capital R, and radius of the void is considered to be small r. So the relationship is like this. So radius of the void divided by radius of the sphere, that is called 0.225. The arrangement, whether the arrangement whatever may be, the what will be the size of the particle, but the radius of the void by radius of the sphere will be remain constant. And similarly, this is the derivation of relationship between radius of the octahedral void and radius of the sphere. So that is called R, radius of the octahedral void divided by radius of the atom, that is radius of the sphere. So the numerator you will find, so it is by mistake it is so again so written void, but actually that is sphere. The denominator you will find R void divided by R sphere, right? R void divided by R sphere, and the relationship it is 0.414, that is constant, whatever that is independent upon size of the sphere. Now coming to calculation of density of a cubic crystal from its structure. Let the length of the cubic unit cell equals to A, and volume of the cubic unit cell equals to A cube centimeter cube, and density of the unit cell equals to mass of the unit cell divided by volume of the unit cell, and volume of the unit cell is A cube centimeter cube. Then mass of the unit cell equals to the number of atoms present in the unit cell into mass of each atom. So that is Z equals to mass of each atom. Then mass of each atom into Avogadro's number equals to atomic mass. Let the atomic mass of the element equals to capital F. So mass of each atom into Avogadro's number equals to atomic mass. So mass of each atom equals to atomic mass divided by Avogadro's number. So now if we put these values, we can write density of the unit cell Z equals to, sorry, rho equals to Z into M by Avogadro's number divided by A cube. So that is rho equals to Z into M divided by A cube into Avogadro's number gram per cc. So this is the formula to calculate the density of the cubic unit cell. So this is the fundamental part of the solid state, and so today we'll stop here. So this is fundamental part of the solid state, and if possible, Next, we'll discuss about the symmetries, solid state symmetry. So today we'll stop here.